Welcome back, Physics 30. This is Unit 1E, Part 4 booklet. Corresponds to pages 98 to 109 of your Do Attain booklet. And the objectives here: recognize the equations for uniformly accelerated motion and the derivation, and solve problems involving those equations. So I'm not going to go through the derivation of this. In your Do Attain, it goes through how graphically each of these equations is determined. On this front page, I'm just going to go through the equations with you, and then the rest of the booklet will be solving problems using those equations, and I will get you to hand this book in for marks. So I'll go over a few questions with you, and then I'll get you to do the rest of it. I will give you final answers though, so you'll be able to see if you're on the right track. Okay, so after reading through pages 98 to 102, you can see where all these equations come from. Some of them we've already seen. For example, acceleration is change in velocity over change in time. And of course, a change in velocity is some final velocity minus an initial velocity. I think previously I've used v2 minus v1. But you can also use final velocity minus initial velocity over a change in time. Now, if we rearrange this equation to solve for Vf, multiply each side by t, and then add Vi to each side, we get this one, which will be useful if we know initial velocity, acceleration, and time, and we're asked to find final velocity. If we subtract at from each side, we can solve for initial velocity. So that would be useful when given the final velocity and acceleration and time and looking for initial velocity. Three other equations here involve displacement. Initial velocity plus final velocity divided by 2. So you're looking for average v times t. So this one's useful if you don't have acceleration, but we have initial and final velocities. This one, initial velocity, change in time plus 1/2 of acceleration times time. This is an equation you would use if we didn't have final velocity, but we were given initial velocity. Quite often the initial velocity is 0 in a lot of questions, so this part of the equation is 0, and the equation just becomes delta d equals 1/2 at squared. And this last one here, if we are not given any indication of time, v final squared is equal to v initial squared plus 2ad. Okay, so those are the 7 equations we'll be looking at. It's useful to get these down so you can refer back to this front page. Other interesting things, what we've been looking at so far in the acceleration section and this velocity section, position time graphs. If you take the slope of a position time graph, you get velocity. And if you take the slope of a VT graph, you get acceleration. So you can see how that's really, the slope moves one to the right. And also in the last book that we looked at what happens when you figure out the area under a VT graph, you get displacement, how far you've moved. So that's an interesting schematic that's going to come into play in the next few booklets as well, when we look at all 3 graphs and comparing them to one another. Okay, some key things when problem solving here. Write down the variables you know, write down the variable that you're trying to solve for, and then choose the appropriate equation from the front page, and then lastly solve for the unknown variable. If you apply those 4 principles in each of these, you'll do fine. Okay, so first question. A horse running at plus 4 meters per second accelerates uniformly to a velocity of 18 meters per second in 4 seconds. What is the displacement during the 4-second time interval? So it's implying acceleration here, but it's not giving an acceleration value. Simply we're going from this velocity to this velocity. So you actually know what the initial and final velocities are. Plus 4 meters per second, plus 18 meters per second. So you can see we're speeding up in the positive direction. Time is 4 seconds, so we're looking for d. We have vi, vf, t, looking for d. So if we go back to the first page here, this equation here would be the one we use. We know all 3 of these variables, so solving for d would be fairly straightforward. So as you can see there, v initial is 4, v final is 18, 4 meters per second. times seconds would give us units of meters. And of course 2 sig figs, so plus 44 meters. That's it. Next question, a car acquires a velocity of plus 32 meters per second by accelerating at plus 4 meters per second squared for 5 seconds. What was the initial velocity? So initial velocity is question mark, because that's what we don't know. We know what velocity it obtained eventually, what the acceleration was, and what the time. So we're looking for VI. We know VF, A, and T. VF, A, and T. Looking for initial velocity. There we go. It's the acceleration equation rearranged for VI. So that will enable us to solve for that part. Final velocity, which is meters per second. Acceleration times time, which is meters per second squared, times seconds. Seconds cancel. You're left with meters per second. So plus 12 meters per second. So you can see these aren't that difficult. The key thing is following those ideas. Write a question mark by the one we don't know. Write the other variables that we do know. A ball falling from rest. Rest always means velocity is 0. Is located 45 meters below the starting point. 3 seconds later. Assuming that acceleration is uniform, what is its value? So we're assuming gravity is pulling this down at a constant rate. Quite often when we're talking about up and down movements, throwing something up in the air is a positive movement, throwing something down is a negative movement. So if you started it here and it fell 45 meters from where it was dropped, 45 meters is in a downward motion. So initial velocity is 0, d is negative 45, t is 3 seconds. We're looking for a. So we know initial velocity, and we're looking for time, or sorry, we're looking for a, we know time. I think this is the equation right here. We know what d is, we know what vi is, we know what t is, we're just looking for a. So delta d equals VIT plus 1/2 AT squared. And you'll see here that since VI is 0, this whole part of the equation will disappear. So when we substitute everything in, negative 45, 0 times 3, 1/2 A of 3 squared. So you can see this part's gone. So we end up with negative 45. And of course, remember order of operations, brackets, exponents come first. So 3 times 3 is 9. 1/2 of 9 is 4.5. So you can see how this nicely works out here. 4.5 times A. So to undo multiply, we divide by 4.5, divide by 4.5. A is equal to negative 10 meters per second squared. Now the number 10 only has 1 sig fig. To show that I have 2 sig figs, I just put this little decimal after the 0. Or I could have put a line over top of that 10. Doesn't matter as long as I indicate 2 sig figs. Okay, there's another question I'm going to do for you coming up, but this one I'm going to get you to do. Here are the final answers. You should copy them down so you can see if you're on the right track. So here plus 45 meters, negative 10 meters per second squared to indicate 2 sig figs. A decimal is placed there. Question 7, the answer will be 7 seconds, 7.0 seconds. Number 8 I'm going to go over with you. A landing plane accelerates at negative 1.5 meters per second squared for 1 minute until it stops. How fast was it going before it started to slow down? So we know acceleration is slowing down. So if we're going in the positive direction, negative acceleration will mean slowing down in the positive direction. Of course, we have to have time in seconds. So 1 minute is 60 seconds. It eventually comes to a stop. So VF is 0, and we're looking for VI. So again, it's going to be this equation that we used earlier, looking for VI right there. We know VF, we know A, we know T. So there we have it, 0, and then subtract negative 1.5 times 60. So we can see a negative, and a negative is going to give us a positive there. So originally going plus 90 meters per second. And of course I put that decimal after the 0 to indicate 2 sig figs. Okay, some final answers for the rest of the questions. So number 9 here, you'll get negative 400 meters per second squared. to indicate 3 sig figs. There's a decimal after that last 0. 10 A and B, plus 25 meters, plus 80 meters respectively. Again, a decimal here to indicate 2 sig figs. C, plus 165 meters. 11 plus 0.200 meters per second squared. 12 is 12 seconds. 13, A is negative 40 meters per second with a decimal there to indicate 2 sig figs. B, plus 800 meters. There's 2 significant digits here, so that line over top of this 0 means we keep the 8 and the 0. Those are the significant ones. And I believe that's it. So go ahead, finish that assignment, and hand it in when you have completed it. Okay, we'll see you again.